Next topic is reflection of plane wave at oblique incidence. So last topic was reflection of a plane wave at normal incidence, and now we can discuss reflection of plane wave at oblique incidence, a more general case. And for that we just need to know some basic formulas. General form for the electric field is given by ERT is equal to E naught cos K dot R minus omega T. And here K and R are two vectors, and K is propagation vector. K is propagation vector. And in last case, in normal incidence and all, we took it as beta. So you can take K as something very similar to beta. And in general case, we take propagation vector as K itself, and K is in vector form. You can write K is Kx in the unit vector Ax plus Ky in the unit vector Ai plus Kz in the unit vector Az. And this is a vector, and the magnitude will be almost the same as beta. It is used in two different scenarios. It's almost the same propagation vector. It's vector K and beta. Modulus of vector K will be beta. Then position vector, vector R is given by Xax plus Yay plus Zaz. And this is the general equation. Okay, ERT is E naught cos K dot R minus omega T. And here you can see magnitude of propagation vector is K square is Kx square plus Ky square plus Kz square. That is equal to omega square mu epsilon. What is this? This is beta square, because we learned beta is equal to omega square root of mu epsilon. So you can take like this, K will be beta itself. Then these are the general equations that is valid for plane wave at oblique incidence, and you need not go for the derivation, but these are derived from the Maxwell's equation. And what are the Maxwell's equation? Del dot T is equal to 0 if we are considering a source free region. If it's free of charge, what will happen? Rho V will be 0, so del dot E will be 0. Then del dot H or del dot B will be 0. Then curl E is equal to, curl E will be minus j omega mu H, and curl H is equal to sigma E plus j omega epsilon E. Okay. And when we take a lossless medium, we assume lossless medium when we deal with oblique incidence. Okay, so lossless medium, as long as we take all these derivations with the assumption that the medium is lossless, we can take sigma as 0. Okay, as sigma is 0, this term will not be there. So curl H will be j omega epsilon E. And from this you can derive this equation relating the fields and K. But how to write, I will tell. Instead of del operator, you can write propagation vector. It's a shortcut to how to remember it. So it will be K dot T is equal to 0. Again, instead of del you write K, that is K dot H is equal to 0. Next, K cross E is equal to, take the complex conjugate. Okay, so here it will be like negative will be replaced, and it will be omega mu H. Similarly, K cross H will be, remove that J and there will be a minus sign, that is minus omega epsilon E. Okay, so these equations are valid when we consider plane wave at oblique incidence. So this is not actually the derivation, and we are not going to the entire step of derivation. From Maxwell's equation, this is a shortcut of how to write the equation connecting propagation vector and electric magnetic field. Vector K dot E is 0, vector K dot H is 0, K cross E is omega mu H, and K cross H is minus omega epsilon E. Okay. How did you write that? for all the del operator, instead of del you wrote k, and when you took these two, third and fourth Maxwell's equation, you took the complex conjugate and removed j component. Okay, so these are the equations that that are valid when you consider plane wave at oblique incidence. And again, this is an example for oblique incidence of a plane wave, because when we considered the normal wave incidence, it was like this, right? It's like this in the incident ray, transmitted ray, and reflected ray in this direction. But here there are different angles that we are considering: theta I, angle of incidence; theta R, angle of reflection; and theta T is the angle by which it is transmitted. Okay, the Ki, it is a propagation vector corresponding to the incident wave, propagation vector corresponding to the reflected wave, and propagation vector corresponding to the transmitted wave. It is Kt, Ki, Kr, and Kt. Theta I, theta R, and theta T. Okay, so how you can write this? It will be cos k dot r minus omega t, and you know k and r. K is this, r is this. So k dot r means kx into x plus ky into y plus kz into z. So that is coming in these three parts. Okay, kx into x plus ky into y plus kz into z. And corresponding to incident, reflected, and transmitted wave, you have suffix I, r, and t. Then minus omega t, again omega I, omega r, and omega t. Okay. So these are the first step is we are writing the equations of electric field corresponding to incident, reflected, and transmitted wave. And you apply the boundary condition. Boundary condition is that the tangential component of E must be continuous across the boundary. And in case of normal incidence, we derived it step by step, line by line. But here we are not going for that. We just check the boundary condition. It is EI of Z equals 0 plus ER Z is equal to 0 is equal to ET Z is equal to 0. And you have to substitute the corresponding values here. And you are actually deriving the condition that should be satisfied, and these are the conditions which are important. If you solve the boundary conditions, you will get that these conditions to be satisfied. First condition is called frequency matching condition, that is equal to omega I is equal to omega R is equal to omega T. That is the angular frequency corresponding to incident wave, reflected wave, and transmitted wave. All these will be same. Exactly same. So omega I is equal to omega R is equal to omega T. This is called frequency matching condition. The rest of the two conditions are called phase matching condition. That is Kix is equal to Krx is equal to Ktx is equal to Kx, and Kiy is equal to Kry is equal to Kty is equal to Ky. That means x components of propagation vectors are all same. Y components of all propagation vectors are same. Okay, so these are called phase matching condition, and this condition is called frequency matching condition. So again, these are applicable in case of plane wave at oblique incidence. Okay, plane wave at oblique incidence. Next, again from that, you get these equations. One is Ki sin theta. Again, there are some derivations in between coming. I will share the notes for the derivation in this here. What I am trying to explain is the things you should know and learn, and the main equations. Derivation part I will share the note. Okay. So here Ki sin theta is equal to Kr sin theta. You get it in 2-3 steps. And the second is Ki sin theta is equal to Kt sin theta t. So what you are going to do is, from the first equation, that is Ki sin theta I is equal to Kr sin theta r. Okay. And I told you earlier, K, how it is related to beta. Modulus Ki will be equal to beta. It is in medium 1, so it will be beta 1. Similarly, modulus of kr will also be equal to beta 1. Why? Because both I and r are in same medium, in medium 1. Okay, so ki and kr both will be equal. Okay, so how you can write beta 1 sine theta I is equal to beta 1 sine theta r. Okay, so sine theta I is equal to sine theta r, and theta I is equal to theta r. So this is one thing you can derive. That is, angle of reflection equals angle of incidence. Theta I is equal to theta r. And now consider the second equation, that is ki sin theta I is equal to kt sin theta t. Here the thing is kt. What is the value of kt? It is in medium 2, so it will be equal to beta 2 because t, that is in medium 2. Hope it's clear. T is transmitted ray or transmitted wave is in medium 2, so kt is beta 2. Again substituting, you get beta 1 sin theta I is equal to beta 2 sin theta t. Okay, and again you know that beta 1 is equal to omega square root of mu 1 epsilon 1. Okay, into sin theta I is equal to omega square root of mu 2 epsilon 2 into sin theta t. Because beta is omega square root of mu epsilon. So beta 2 is omega square root of mu 2 epsilon 2, and beta 1 is equal to omega square root of mu 1 epsilon 1. And you substituted in this. So this equation you got from this first equation, and you are deriving the second equation from equation 2. Okay. So here you got till this. And now there is one relation connecting the refractive index. And refractive index n is equal to, so omega gets cancelled, and you multiply with c. Multiply on both sides with c. So you can write c square root of mu 1 epsilon 1 into sin theta I is equal to c square root of mu 2 epsilon 2 into sin theta t. This term c square root of mu 1 epsilon 1 is called n1, c square root of mu 2 epsilon 2, that is n2. These are refractive index of medium 1 is n1 and of medium 2 is n2. Refractive index. Okay, so this can be written as n1 sin theta I is equal to n2 sin theta t. Okay, so this is the second equation. n1 sin theta is equal to n2 sin theta t, and this is called, what is this? This is called Snell's law. So you derived two equations. One is sin theta is equal to theta, that is angle of incidence is equal to angle of refraction, and the second equation is or theorem is Snell's law, which states n1 sin theta I is equal to n2 sin theta t, where n1 and n2 are the refractive indices of medium 1 and 2. Okay, so these are something which you should know or learn generally in case of reflection of plane waves at oblique incidence, and I have just mentioned the main points or the main equations in a derivation. The complete flow of the derivation I will be sharing the notes. Okay. So next, there are two terms that you should learn. That is, one is plane of incidence. Plane of incidence is a plane defined by the propagation vector and a unit vector normal to the boundary. So when we consider a boundary for a wave, that boundary will be perpendicular to plane of incidence, because plane of incidence will be carrying, or it will have two vectors. One is the propagation vector, that is the direction in which the wave is traveling, and the unit vector, that is normal to the boundary. So how can you define a plane of incidence? Plane of incidence is a plane that contains both propagation vector and the unit vector that is normal to the boundary. That is called plane of incidence. And angle of incidence is angle between propagation vector and the unit vector normal to the boundary. Okay, so angle between K and AN is given by angle of incidence, and plane of incidence is a plane that contains propagation vector and unit vector normal to the boundary. So these are the two terms which you should understand. Now, you have two, in oblique incidence there are two types. One is parallel polarization and next is perpendicular polarization. And you just go through this. Parallel polarization means electric field is parallel to plane of incidence, and in perpendicular polarization E is perpendicular to the plane of incidence. Okay, so in parallel polarization E is parallel to plane of incidence, so M, magnetic field, or H will be perpendicular. So that's why it can also be called transverse magnetic polarization, because E is parallel in case of parallel polarization. E is perpendicular to plane of incidence in case of perpendicular polarization. So you should learn those terms. Parallel polarization means E parallel to plane of incidence. Perpendicular polarization means E perpendicular to plane of incidence. Okay. And you can go through the figure. Okay, parallel polarization means, what did I say? Parallel polarization means vector E is parallel to plane of incidence. Okay, so what is the direction? So here plane of incidence will be here. Plane of incidence will be XZ plane. Okay, XZ plane is the plane of incidence. And you can see that the electric field, this shows that these are the vectors corresponding to H. Okay, so H is perpendicular to the plane, so H perpendicular and E parallel. So E parallel means that is parallel polarization. E is parallel and H is perpendicular. You can see both these notations show that the vectors are perpendicular. So H is perpendicular whereas E is lying in the plane. E is parallel to the plane of incidence. In all these cases, E and propagation vector and E both are lying in the plane of incidence. So this is an example for parallel polarization. And in case of perpendicular polarization, first we'll go through the figure. Here you can see that vector E is perpendicular, right? Here you can see that vector E is perpendicular to the plane. So perpendicular polarization means E is perpendicular to plane of incidence. E is perpendicular to plane of incidence in perpendicular polarization. E is parallel to the plane in case of parallel polarization. Okay, and now you have two equations to learn. That is, this is reflection coefficient. Okay, reflection coefficient, we will derive the equation for reflection coefficient in normal incidence. Here what happens is you have separate equations for parallel as well as perpendicular polarization. So reflection coefficient is given by this symbol, that is ER naught by EI naught, which is equal to eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. Eta 1 and eta 2 are the intrinsic impedance for medium 1 and 2 respectively. And this is transmission coefficient. Transmission coefficient. So transmission coefficient corresponding to parallel polarization, Et naught by I naught, that is equal to, in both cases the denominators are same, eta 2 cos theta t plus eta 1 cos theta I, and numerator it is 2 eta 2 cos theta t. So these are the equations. So these are important, and these equations are called Fresnel's equations. Okay, these equations are called Fresnel's equations. And this is I. Okay, it is 2 eta 2 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. Okay, so you have to learn these two equations, and this is valid only for parallel polarization. It is not same in case of perpendicular polarization. And another equation, in normal incidence we learned 1 plus reflection coefficient is transmission coefficient. Here it is 1 plus reflection coefficient is transmission coefficient into cos theta by cos theta I. This is also valid only in case of parallel polarization. Okay, so hope the equations are clear. Here both denominators are same. I will write it again. I think I and T is not that clear. So reflection coefficient corresponding to parallel polarization is eta 2 cos theta t minus eta 1 cos theta I divided by the same terms in denominator also, eta 2 cos theta t plus eta 1 cos theta I. This is the equation for reflection coefficient. And transmission coefficient corresponding to parallel polarization, it is 2 eta 2 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. These are the two equations corresponding to parallel polarization. These are also called Fresnel's equation. And 1 plus reflection coefficient corresponding to parallel polarization is transmission coefficient into cos theta t divided by cos theta I. So these three equations have to be learned in parallel polarization. Next is another important term, that is Brewster angle. Okay, Brewster angle, the definition is angle of incidence for which reflection coefficient is 0. For which angle of incidence reflection coefficient is 0. Reflection coefficient is 0 means ER naught by EI naught is 0, or there is no reflection. So that case, the corresponding to which angle of incidence that happens, that is called Brewster angle. So what is the equation corresponding to reflection coefficient in parallel polarization? It is eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. So this is the equation. And for this to be 0, theta I will be theta b parallel. Okay, so taking the numerator, you can write eta 2 cos theta t is equal to eta 1 cos theta b parallel. Okay, because reflection coefficient is 0 when angle of incidence is Brewster angle. So how you can write that? Cos theta b is equal to so this will be cos theta b is equal to eta 2 by eta 1 into cos theta t. Okay, again on substituting, you will get the final answer as theta b parallel is equal to sine inverse square root of 1 minus mu 2 epsilon divided by mu 1 epsilon 2, the whole divided by 1 minus epsilon 1 by epsilon 2 the whole square. So this is the equation. Okay, and all these entire term comes under the square root. Okay. So theta b, Brewster angle corresponding to parallel polarization, is given by sine inverse square root of 1 minus mu 2 epsilon divided by mu 1 epsilon 2 divided by 1 minus epsilon 1 by epsilon 2 the whole square. Again, one more assumption is coming. We generally consider oblique incidence in medium. In which type of medium? Lossless medium. And one more thing happens, that is mostly the mediums are non-magnetic. Okay, that's also a common situation. That's in practical cases, most of the practical cases, the medium will be non-magnetic. So, non-magnetic means mu r will be equal to 1. So, again you can eliminate this, because mu naught, when mu r is 1, both mu values will be mu naught. So, how you can write? You can write theta b parallel is equal to sine inverse square root of 1 minus mu naught epsilon 1, as it is a non-magnetic medium, divided by mu 0 epsilon 2 divided by 1 minus epsilon 1 by epsilon 2 the whole square. These two get cancelled. So this is a minus b, and denominator it is a square minus b square. So this can be written as a plus b into a minus b form. So again it can be simplified as theta b parallel will be sine inverse square root of 1 divided by 1 plus epsilon 1 divided by epsilon 2. This is valid if the two mediums are non-magnetic in nature. So this is a simplified equation corresponding to non-magnetic medium, and this is the general equation for Brewster angle in case of parallel polarization. Hope it is clear. The definition for Brewster angle is the angle of incidence at which reflection coefficient is 0, and you directly substitute and you should get the final equation like this. And second assumption is that most of the medium are non-magnetic in nature. So mu1 and mu2 both will be equal to mu naught, and you will get the equation simplified in this form: sine inverse square root of 1 divided by 1 plus epsilon 1 by epsilon 2. This is applicable only if the medium is non-magnetic in nature. Next, perpendicular polarization, we deal in the same way, and you will get the equations like this. You have to learn these two equations corresponding to reflection coefficient and transmission coefficient, and in case of perpendicular polarization this is valid. 1 plus reflection coefficient is equal to transmission coefficient in case of perpendicular polarization. This is true in case of perpendicular polarization. Okay, and these are the two general equations. There is difference. You can compare between parallel polarization and perpendicular polarization. And again, coming to Brewster angle, in case of Brewster angle, the equations are, you got reflection coefficient as eta 2 cos theta I minus, this is the equation. So this term should be 0 for calculating Brewster angle. Okay. So eta 2 cos theta B perpendicular will be equal to eta 1 cos theta T. So cos theta B perpendicular will be equal to eta 1 by eta 2 into cos theta T. Again, on substituting, you get this. Okay, you get like this, and that is theta B perpendicular will be equal to sine inverse square root of 1 minus mu 1 epsilon 2 divided by mu 2 epsilon 1 divided by 1 minus mu 1 by mu 2 the whole square. So this is the general equation for Brewster angle corresponding to perpendicular polarization. So this is the equation for Brewster angle corresponding to perpendicular polarization. And again, we know that in many cases mediums are non-magnetic in nature. So what will happen? This can be written as theta b perpendicular will be equal to sine inverse square root of 1 minus epsilon 2 by epsilon 1 divided by 0. Okay, so division by 0 means it is infinity. So sine inverse infinity means it will be an infinite value. Okay, so again the thing is like it does not exist. So what you can it won't exist, sine inverse infinity. So what you can say is Brewster angle does not exist for perpendicular polarization. Brewster angle does not exist for perpendicular polarization. Okay, so why this happens? Because this value is infinity. Okay, and it does this part is infinity and this value does not exist. And mathematically you can write the equation like this: theta b or Brewster angle corresponding to perpendicular polarization is given by sine inverse square root of 1 minus mu 1 epsilon 2 divided by mu 2 epsilon 1 divided by 1 minus mu 1 by mu 2 the whole square. Okay, so in oblique incidence we discussed two types. One is parallel polarization and the next is perpendicular polarization. Parallel polarization means electric field is parallel to plane of incidence, and in perpendicular polarization electric field is perpendicular to plane of incidence. That is one thing, the definition. Then you have to learn the equation separately for reflection coefficient, transmission coefficient, Brewster angle, and also relation connecting reflection coefficient and transmission coefficient.